What was your area of research?
It was extrusion processing.
Okay. Okay.
Yeah, under agriculture engineering department.
Okay.
It's the biosystem engineering and food engineering, you can say.
Yeah.
Yeah.
So it's
So,
already 5 minutes to 9:30, so we can begin the session. So a very
yep.
warm good morning to all the participants on the platform. As we all know that under IDP-NAHEP, which is Institutional Development Plan of National Agriculture Higher Education Project, a World Bank and ICR funded project which is being run at GB Pant University is one of the prestigious projects that is basically focusing on enhancing the cognitive skills of the students, undergraduate students. And in the series of workshops, trainings, and interactive guest lecture, we are trying it hard to make it a point that yes, foreign faculty, those who are having expertise and those who are distinguished in their field, in their respective fields, are able to give exposure to our students so that our students are able to find a definite pathway towards their career, and that can help them out in getting the advanced knowledge related to their field. And in this series, because we have been contacting many foreign experts, so Dr. Manoj Karkee sir, who is there on the platform for today's expert, and will be speaking on AI and robotics in agriculture, is there with us all the way from Washington State University. So I welcome you, sir, on behalf of IDP NHEP Pantnagar. And as we all know that the application of automation, as soon as the automation came into agriculture, it completely revolutionized agriculture. And agriculture 4.0 is the age that we today as agriculturists and allied scientists are witnessing. So without waiting and without letting the expert wait for a few more moments, I personally request Dr. UC Lohani sir, who is one of the project scientists under the IDP-NAHEP project, to welcome the participants on the platform and to briefly state the profile of today's guest so that we can have know how exactly what kind of stature, because already when we expect that we are having some alumni on our platform, we always want to have some interaction, we always want to have some profile of there. So I request UC Lohani sir to briefly read the profile of today's expert, Dr. Manoj Karkee sir, please.
Thank you, Deepthi. From my side, a foggy morning to all of you. It's fog here. And to a very good evening to Dr. Karki. I welcome Dr. Karki. Thank you for accepting our request and delivering your talk here. I welcome all the participants for this third talk under this theme, you can say, role of agriculture engineering in world market. So as you can see that Dr. Karki is expert in AI and robotics in agriculture, and he is presenting today's presentation on that topic. So I hope that all the participants will get the benefit from this talk. It's my privilege to take the opportunity to introduce our today's expert. Dr. Kaki is an associate professor in the biological system engineering department at Washington State University. He was born and raised in the eastern hill of Nepal. He received his diploma in civil engineering and undergrad in computer engineering from Tribhuvan University, Nepal. His MS was in remote sensing and GIS from Asian Institute of Technology, Thailand, Bangkok. And his PhD was in agriculture engineering human computer interaction from Iowa State University. Dr. Karki leads a strong research program in the area of sensing, machine vision, and agricultural robotics at the WSU Center for Precision and Automated Agricultural Systems. He has published widely in such journals as Journal of Field Robotics, Computers and Electronics in Agriculture, and Transactions of the ASABE, and has been an invited speaker at numerous national and international conferences and universities. Dr. Karki is currently serving as an elected chair for International Federation of Automatic Control Technical Committee, Control in Agriculture as an associate editor for Transaction of the ASAB, as a guest editor for Sensors and editorial committee member of Information Processing in Agriculture. Dr. Karki was awarded 2020 Railbird Engineering Concept of the Year by American Society of Agricultural and Biological Engineers. and was recognized as 2019 Pioneer in Artificial Intelligence and IoT by Connected World magazine. So what a sound profile he has. So hopefully with this profile, we are coming here to hear him with the advances in AI and robotics and agriculture so that we can have some concept and to take them in future in our research work and in our career. So thank you, Dr. Karkee, once again. And we are waiting to hear you with your talk. Thank you, Deepti. You can move forward now.
Well, thank you, sir. We obviously know that the discipline which we are aligned to, we must be acquainted with the advanced knowledge, with the recent things that are coming in terms of technological intervention, in terms of research and development in any field. And as a professional, it's our duty to get acquainted with all those things. And today, as we have got this session for us, we have got an opportunity, an excellent opportunity, I must say, to get into the research and development, to get into the core of agriculture 4.0. So I invite Manoj sir for his deliberation, please.
Thank you very much, Dr. Lohani and Dipti, for your wonderful introduction. And I really appreciate this chance, this opportunity to share some of my thoughts in terms of what I'm doing and where we might be going in the future in the area of agricultural automation and robotics in agriculture. I would like to especially thank you, Dr. Lohani, for the invitation and giving me this opportunity again. So my name is Manoj Karkee. I'm working at the Center for Precision and Automated Agricultural Systems at Washington State University. Before getting into the presentation, I would like to briefly talk about the center itself and our location and why we are located where we are located. So as we look at this US states map, Washington State is in the top left corner, as we can see. Sometimes audience from foreign countries are confused between Washington, D.C. and Washington State. We are actually in the other side of the United States in the Pacific Northwest region, right under Vancouver of Canada. In the Pacific coast, whereas Washington, D.C. is in the Atlantic coast, right in the east side of the country. This state is really green in most of the areas, but the central part of the state is quite dry and really low precipitation. Our center is located somewhere at the south central part of the state. As you can see pass here. This is located strategically here in the kind of a arid area where we have a lot of river water flowing down through Columbia River and Yakima River and other rivers, and have been used very efficiently to produce a lot of high-value specialty crops such as apples and cherries and pears and such. And that's why we're also located here in the center of this specialty crop region in the state of Washington. We're about 3 hours away driving distance from Seattle and about 2 hours away from Pullman, Washington, which is the main campus, the main university campus for Washington State University. As I mentioned earlier, these are some of the important crops for the state: apples and cherries and pears and wine grapes and juice grapes and wheat and some other crops, as you can see here. So now let's talk about AI and robotics in agriculture, some thoughts behind how these technologies, concepts, algorithms are connected together to help us be better in terms of leading agriculture to, as Dipti mentioned earlier, 4.0. So what these interactions bring to us is the capability to make and implement farming decisions with increasingly desirable outcome over time. And that's, in my opinion, what smart farming means. these technologies, when they interact and work together, will provide us this capability to assist in producing more or better or both with as little as possible. When I say that, as little input as possible, such as labor, nutrients, water, and such. But we need to also be able to do this without compromising the potential of future generation to do the same, which is the concept of sustainability, as we know, is that we need to be able to achieve our goal for the current generation without compromising the goal for the future generation, or the means and the resources for the future generation to achieve the same goals. So to achieve these capabilities, artificial intelligence and cyber physical systems, CPS, I have bubbled up here in the middle, worked together and interact together closely, leading to from some fundamental concepts of machine learning, such as deep learning and expert systems, predictive modeling, into some technologies such as pattern recognition, machine vision, big data analytics, decision support, and robotics. So these are the technologies that benefit from and are developed by using fundamental AI principles and the infrastructures and the facilities or features provided by cyber physical systems. Now, these technologies such as machine learning and decision support systems could be used to achieve certain outcomes or certain certain aspects or operations in agricultural field. It means a lot for us in agriculture when we have these kinds of technologies available to perform plant condition and environment reception, perception, understanding, make farming decisions, implement decisions that we are making in terms of certain things that need to happen in these fields, and analyze the outcome after certain treatments or certain actions are taken in the field. How does that action change the field or the crops or anything that we're doing in the field? And that kind of outcome must be analyzed, and CPS, the cyber physical system, and the technologies we mentioned, including machine vision, decision support system, and big data analytics, would help us perform those kinds of operations in the field. Now, where does it help? Actually, there is everything that we do in the field could benefit from these kinds of technologies, and the tools these technologies enable us to develop. For example, we can be more efficient with water and nitrogen management. We could be more efficient and effective and timely in identifying and monitoring and managing pests. Same thing with CANOPY management, harvest and post-harvest managements, and things like that. So in such a way, artificial intelligence, robotics, and cyber physical systems interact very closely together to help us be better in managing resources so that we can achieve the goal of producing more and better quality food and other agricultural products with as little input as possible. So with that behind, kind of a general overview of how these recent advancements in AI and other technologies help us in farming, let me get back into the nitty-gritty of today's presentation that deals mostly about robotic and automated systems for what we call specialty crops. When we say specialty crops, it includes fruit crops and vegetables and nursery crops and such. So before even getting there, though, I want to just start with this statement that mentions that agricultural mechanization was recognized as one of the most important achievements of 20th century. I think it was recognized as number 6 or number 7 out of 100 achievements recognized. That's because the machinery system and farming systems that we have developed over the last 100 years have transformed agriculture substantially, in a way, radically. It may not be the same case, or it may not be similar to all the countries out there in the world. However, a lot of developed and developing countries have transformed their agriculture to a new height over the last 100 years. Because we developed these machines and systems. For example, in the United States, in the last 100 years or so, the population involved in farming has gone down from about 90% to less than 2%, while producing much more than what the population have been producing 100 years ago. USA is one of the biggest exporter of agricultural products around the world, which is again achieved by only 1% or so of the population being involved in farming, because we have these machinery and agricultural systems developed over the past 100 years. Some examples here: tillage machines like these used to plow field and hundreds, at least thousands and thousands of acres covered every day. Planters like these, several of them can work together in swarm kind of configuration, covering large fields. Sprayer technologies such as these ones for row crops such as corn and soybean and rice, row crop harvester like this for again corn and soybean and wheat, sugarcane harvester like this. In addition to those mechanization or mechanical or mechanized systems, we have also developed and adopted automated systems such as guidance and auto steering for tractors. These kinds of GPS guided tractors have been commonplace in the farming operations around the world these days. I was reading somewhere that more than 70% of the tractors that are produced currently have the capability to use this kinds of auto steering system, and farmers are widely using these kinds of technologies to follow some straight or predefined curved paths or trajectories to do some field operations such as planting, plowing, harvesting, and such. However, the benefit of these kinds of technologies have been to only certain kinds of crops. As we can see here, the crops that I discussed earlier, the ones I mentioned earlier, specialty crops, have not been benefited by these kinds of advanced technologies even now. For example, apples. The way we harvest apples have not evolved at all ever since how we knew how to build these ladders and little baskets or bags to carry fruit up and down these ladders. As you can see on our left is a picture taken a long time ago, about 80 years ago, down in Virginia, and one on our right is a picture we recently captured in the state of Washington. Other than the color, nothing is really different between these two pictures. The way we use those ladders and the way we climb up and down the ladders with these bags, picking fruit up and down, picking fruit while climbing up and down, putting them onto these bags when they're really heavy, like 20-30 pounds. This is like 15 kg, 10 to 15 kg. We bring them down, empty on these bins. So this process hasn't changed, and I believe with the advancement in artificial intelligence, robotic technologies, sensing technologies, computational infrastructure, all these recent advancements, I think we have positioned us to be better in terms of using automated machines to do some of these really harsh and labor field operations. It's not that I just started working in this area. There have been long research and development in the past to develop robotic solutions, automated solutions for various operations in specialty crops, including harvesting, like apple picking, as we saw in the previous slide, the challenge that we saw there. However, there has been limited commercial success in this specific area of research and development. There are a few limitations why we are facing challenges to hit the commercial adoption of these machines. Some of those, the major ones, in my opinion, include speed, accuracy, and robustness, or to be specific, their lack of those features. We don't have machines as fast, as accurate, and as robust as we would like them to be for practical adoption in field conditions where agriculture occurs. Robustness, for example, mean something like we may have many different varieties of apples. If we're developing an apple picking machine, it needs to be able to pick apples in different kinds of trees, different varieties. Some are red, some are semi, some are even green. How could we develop a machine that works in all these kinds of situations is one of the challenges. Produce plant damage is another challenge. For example, when we are shaking fruit from trees, that's some technologies invented and evaluated in the past have been limited by the damage they cause to plant and fruit. Cost and lack of adoption. Agriculture runs, as we know, in a really thin margin, and the technologies we develop must be affordable to the growers. Otherwise, they would not be adopted. And if they are not adopted widely, the economy of scale goes against the cost reduction aspect of it, and it makes the technology even more expensive. And that's why we need to be able to break that cycle of high cost and low rate of adoption. So to address some of these challenges, WSU CPAS program on agricultural robotics that I lead have been looking at, or has been rather looking at, a few different fundamental as well as applied aspects in agricultural automation and robotics, with the hope that we can address some of those challenges around speed, accuracy, and robustness, as well as practical adoption and things like that. So one of the areas of our research and development have been apple and cherry harvesting. We have been looking at both what we call mass and robotic harvesting. By mass, what I mean is that some technology that harvests multiple fruit at a time. And different types of robotic harvesting is kind of obvious. We target one fruit at a time and pick it. Different types of end effectors, like if it is a robotic picking, do we want to use soft material? Do we want to use 3 fingers or 5 fingers? Do we want to use tandem operated fingers? Things like that. And different catching mechanisms for mass harvesting systems. We are trying and experimenting with multiple layers of catching mechanisms, different kinds of foam material to capture fruit and things like that. And then we integrate these technologies into a robotic system and evaluate different kinds of those robotic systems in performing different field operations. One of the examples is here, automated cherry harvesting. We have been developing big machines like this. I would have to rather say we are advancing some of these mechanical harvesting systems, like the one we saw here in the middle, to harvest cherries, collect them in the bins like what we see here. And we're also using a machine vision system to capture images both in day and nighttime condition, identify where the branches are, even under the situation where the branches are completely or partially occluded by the fruit and leaves, as we can see in this particular image. And then once we are able to find where these branches are and estimate the trajectory of these branches, will be able to go grab those branches automatically using the robotic system and shake the cherry off from these trees. Another particular focus has been in developing robotic harvesting solutions. I'll let the audience see these videos for a minute or so. So what you saw in the left side is the laboratory and field evaluation of a single arm robotic system that was developed and experimented and evolved at the lab that I lead at Washington State University. With this robotic system, we went through a couple of different prototypes, improved over time in the last like 5, 6, 7 years. And then once we knew what is possible, once we learned some knowledge, some generated some novel concepts and ideas and prototypes, we started to collaborate with a company out of Israel called FF Robotics. The machine we saw on our right is a machine primarily developed by the company as in terms of its mechanical system and everything that we see there. This machine has 12 arms, 6 on our left, 6 on our right, so that this machine can harvest apples from both sides of the machine, covering one half of the tree in one side and another half of the tree is in the other side. And these apples are collected onto a container bin. It's been very promising technology. It's been tested in the commercial orchards here in Washington and Israel. And the company is working really hard to provide a commercially viable solution for farmers around the world. We have been again collaborating with this company to improve the overall harvesting process, improve the machine vision system, and various other aspects of this machine. In addition to the robotic system, we have been also looking at, as I mentioned earlier, mass harvesting system. In this specific video, we'll see a unique or novel design of a multi-layer second catch harvesting system. We call it a targeted second catch because it targets to a small section of the tree or a small branch within these tree canopies at a time, so that when we shake them, we can shake gently to release the fruit and catch them or capture them right under where they are, so that these fruit are not flying everywhere. These fruit are not hitting each other very hard, and we could maintain the quality necessary for the fresh market industry, where quality is a really important parameter. So anyway, we have achieved really good harvesting and fruit quality outcomes with this machine for certain varieties. This is really dependent on the variety, because some varieties are really susceptible to impact, whereas others are slightly tougher. And this system again is working quite well for a couple of varieties such as Jazz and envy, I believe, and there are certain issues with other varieties such as Gala and Honeycrisp. But for some of these varieties, this machine shows to be a really promising system compared to even robotic picking, because this the harvesting efficiency, or let's say the throughput of this machine, will be much higher than a robotic system, and it could be a much cheaper solution for growers compared to a robotic picking machine. As I mentioned, there are certain kind of constraints. This works with certain architecture of the trees and certain varieties, but for the ones that it works in, it will be a much more affordable solution compared to a robotic system. And that's why in my research program, we are pushing both kinds of technologies forward simultaneously, because I believe there is a complementary nature of these two technologies. The robotic system could be applicable to high value crops such as Honeycrisp and Sweet Tango and Cosmic Crisp, the newer variety that Washington State produced or marketed just a few years ago. In those kinds of apples and some other high value crops, maybe robotic system is applicable. For some of the other commodity varieties where the market value is not as high as Honeycrisp or Sweet Tango, we might be able to use these kinds of machines. So, and also there are other markets such as cider apples and some other processing fruit that this machine could be would be able to harvest without any issues, because damage in those kinds of fruit, the fruit destined for processing markets such as juice and jam, would not or would tolerate more damages to the fruit than the fresh market industry, as I mentioned earlier. Now let me switch the gear towards canopy and crop load management. In addition to harvesting systems, we are working on various other robotic solutions for apple and cherry and some other fruit crops, including robotic pruning, robotic pollination, and robotic thinning. I don't know how many in the audience have a background on fruit crop production. Every year, these fruit crops need to be pollinated, certainly naturally by bees and other pollinators. These trees need to be, or some of the branches in these trees need to be pruned out every year to maintain the health and to remove the ones that are not productive, and facilitate the growth of new branches that could be productive in the future. And thinning is another aspect of overall canopy and crop load management, where we remove a portion of flowers and a portion of green fruit every year, so that the remaining fruit become or meet the quality and yield standard, or the desired quality and yield that farmers are looking for, so that they can market this fruit to their target markets. So in this area, we are working on all of these three aspects. We are developing machine vision system that can image canopies both in the dormant, flowering, and growing season. And we use deep learning and other machine vision techniques to identify the target objects that we'd like to identify. For example, if it is robotic pollination or thinning, we'd like to find and locate where flowers are. If it is robotic pruning, we'd like to find where the branches are and identify the branches that we'd like to prune out. And then if it is a harvesting system, as I mentioned earlier, certainly it would include identifying and locating apples or other fruit. Anyway, once those objects are identified, we also have to develop certain strategies to do something about it. If it is thinning, we need to go remove part of the flowers using robots. If it is pruning, we need to go find those branches and cut them out. If it is pollination, we need to spray some pollens on top of these flower surfaces at targeted locations. All these strategies are being developed in our lab, and we're also developing an integrated solution with end effectors specific to specific operations, such as if it is a pruning system, we are developing scissor kind end effector and some other kinds of end effectors so that we can go cut those branches. If it is a flower thinning, we are looking at water jet and some other techniques to remove some of the flowers. If it is a robotic pollination system, we'll be looking at, actually we're looking at currently some spray nozzles that can spray pollens onto those flower surfaces. As an example, here is a quick video for the robotic pruning that was tested in the lab. I'll let you guys watch this video for a few seconds. I just want to add that this video has been slowed down. Not the video, actually, machine has been slowed down to maintain safety in the lab operation. This robotic arm can be much faster than what we see right now, but this demonstrates the capability of finding where branches are. In this case, certainly in a mock-up tree, tested in the lab, it can go find those branches, cut them off, come back to home location, go to another position, and continue pruning other branches. So this was a lab test, and I have been kind of saying it for last several months, almost maybe more than 6 months now, that we'll be testing it in the field. But finally, my team is ready to go to the field tomorrow, actually. I'll be in the field tomorrow to bring this machine to prune apple or cherry trees, something like what we see on our lower left corner, those kinds of trees in dormant season, which is right now. So we'll be testing this machine, see how much we could do in the field, and over the next couple of years, we'll be improving it to make it better. Another example here for red raspberry crop. We have developed a robotic solution to find where these canes are, bring them together, bundle them, and tie certain kind of taping mechanism to tape these canes around so that we keep the bundles strong, firm, and upright for the fruiting to occur and for the harvesting machines to work efficiently. Here is a quick video of how it works. There is a machine vision system that finds where these canes are, and there is an auger system that goes around the canes and brings them together. And a taping mechanism you can see operating right now. Another example of our robotic and automated system development work include green shoot thinning in vineyards. We have developed a machine vision system that would find out where the cordons are in these wine grapes. The cordons are the horizontal permanent structures in these wine grape canopies in the kind of system that we see here, where there is a trellis wire horizontally placed on which these cordons are trained to. And in the early growing season, we see green shoots coming up from these cordons. As you can see, first week of growth, a few shoots on our top left corner. As you go to the top right corner, there are more green shoots, second week of growth, and then third week of growth and fourth week of growth. In this kind of situation, green shoot thinning is a process of removing a certain proportion of these green shoots so that we can have only desired amount of crop in these vines. If we have a lot of crop in these vines, a lot of clusters of grapes in these vines, we're not achieving the target quality for the kind of wine they want to produce or kind of juice they want to produce. So in this case, we want to find out where the cordons are, and then we want to send a machine that would automatically rotate some rollers around those cordons so that some of the green shoots could be removed. Here is an example outcome of the machine vision system. And it finds out where the trunks are, even under these canopies, under the situation when the green shoot blocks the view to these horizontal cordons. Similar to the cherry harvesting system we have developed, we use certain technique to find out these cordons even when they are not visible. We have tested a robotic system to actually do the thinning operation. I couldn't have a video right now due to the time limit and other things, but we have a machine already performing that at a prototype level. Another example here of a robotic system we have developed is the robotic weeding in onion and carrot crops. A vegetable crop industry in Washington is also very important for us, and we're developing some of the robotic solutions that are really essential for these growers. This system automatically distinguishes where the crop plants are and where the weeds are, and then there is a precision nozzle system that applies a certain chemical on top of the weeds so that those could be precisely killed. It could be also using a precise mechanical solution to remove those weeds, particularly for organic systems where chemical application is not is prohibited. Another example of our research and development include application of unmanned aerial systems or drones in agriculture. In this specific example, we see a bird deterrence system. We have used these drones to fly around vineyards and orchards and blueberry fields, and have seen a substantial reduction in bird activities compared to when these kinds of drones are not flying. Another project we are working on is called Smart Irrigation. In this specific project, we're trying to use all kinds of data, historical information, weather information, as well as various decision support tools, including big data analytic techniques, to reliably estimate water needs in wine grapes and some other crops and apply the right amount of water at right time at right location. Finally, last 1 or 2 slides about the projects that we're working on. Decision support tool for precision orchard management is one of those recently funded projects. We are trying to develop kind of a machine vision system and sensing system in general that will be able to detect the differences between individual trees in the orchards and apply nitrogen and other nutrients and chemicals as desired by the individual trees, rather than applying uniform doses of them throughout the orchards. And we have seen a huge variations in the need of these trees. For example, in terms of nitrogen application, we see a huge difference in the needs of these trees that is indicated by the color of these leaves. And that kind of information could be used to make variable rate nitrogen application decision quite easily, hopefully, as we continue to develop this project. Finally, we have been also working on mobile app-based solutions for farming. It involves a couple of aspects right now: counting and crop load estimation in apples and wine grapes, as well as detecting viral disease and differentiating viral and non-viral symptoms in vineyards. These are some of the efforts going on in my lab around mobile app for crop load management. So with that, I think we're closer to the end of the session. I'll take another couple of minutes talking about a few future directions I believe that we're headed to. We have been talking about mechanization for more than 100 years. Recently, we added automation and robotics into the mix. And we have been also talking about precision farm management for a number of decades. All these, when are integrated together in a way supported by AI and decision support systems, I think it leads us to what we call smart or intelligent agriculture, or agriculture 4.0. And I think this is the direction. We'll continue to develop automated, robotic, and precision management solutions and mechanize as much of the farming operations as possible so that automate, not only mechanize, but automate as much as farming operations so that the farming decisions and implementation of those decisions become increasingly beneficial to farmers, increasingly more appropriate and more accurate and reliable over time. Challenges and opportunities, particularly for small scale farming, which might be to some extent relevant to countries like India, Nepal, a lot of developing countries in Africa and other parts of the world, where I think I believe we are constrained by conventional crops and cropping practices, difficult field terrain in some countries, some areas, land fragmentation and farm size has been a big issue in various countries, labor migration to cities or to even other countries, like a lot of labor going to Middle East from countries like Nepal and India and Bangladesh and Pakistan and some other countries, limited availability and higher cost of farming resources such as irrigation, water, fertilizer, labor. So these are some of the constraints we face in farming, particular to various countries with small scale farming operations. What are the opportunities? I think in these kinds of farming operations, we have a big opportunity to improve the productivity and farm gate value. Breeding of local varieties, improved cropping systems. I'm certainly going outside of my area of expertise here, but I believe these are some of the areas we could make an impact on. Biology versus technology has been the, in a way, notion of the past. I think now we need to combine biology and technology and develop solutions in an integrated and systematic way so that we can deal with these complex systems from multiple perspectives, multiple expertise coming together. Wider research and extension services and access to and efficient use of farming resources such as water and labor. I think if I can say that, I don't know much about the Indian situation, but if it were for Nepal, irrigation water in itself, I think, is the biggest challenge because there are majority of farms in Nepal relying on rainwater, no irrigation system in place, making farming really uncertain, unreliable, and oftentimes a business of loss, and that's really challenging situation. Increasingly affordable technologies and technology modularity are other opportunities. What I mean by that, increasingly affordable technologies. Certainly, complex machines like robotic machines are or can be expensive, but with increasingly affordable computational speed, increasingly kind of cheaper in a way, or decreasing cost of some of these technologies such as drones, and also technology modularity, meaning in the past we'd be developing tractors costing like $300,000, $400,000, $500,000, maybe $1 million. These days we are looking at robotic solutions that may cost much lower, smaller machines, so that small farmers can buy a few of those, whereas the big farmers could buy as many as they needed, so that we could have these technologies possibly adopted by farmers with different scales of operation. Ways for technology adoption. A couple of things that I want to share. It may be of relevance to the Indian situation as well. Cooperatives and neighbor networks might be helpful, which might be already in place in many parts of the world, including India. If the machines are really expensive and a single farmer cannot afford it, cooperatives and neighbors network might help. Identification and application of affordable technologies such as drones, smartphone-based technologies. Novel solutions. Oftentimes, we cannot directly use the technology developed in, for example, waste for big farms, like the robotic harvesting solution that I talked about. But maybe there are ways we can adopt and perhaps develop a local solution that might be inspired by these big machines, like a small automated system for hillside farming, and attract young generation to farming. I think this is a big deal. I think around the world, farming is not always as attractive. Most of the young kids would like to go to other industries, such as, let's say, computer science or engineering or medicine, and do business or profession, or create industries in that kind of sectors, not in agriculture. And I think with robotics and automated systems, we have at least some motivation to bring young generation into farming. Last slide or so, knowledge and technology sharing is a big deal in terms of how we learn from each other, how we help each other. I don't believe in the concept of technology and knowledge transfer. I don't think transfer is the best thing. Actually, it is sharing. We know something in the West. There is a lot of knowledge and know-how, technologies and experiences in the farming communities and the research communities around the world, specific to that specific location or the context. And I think if we collaborate between East and West, North and South, from developing and developed countries, I think we can help each other through things such as summer schools and cert courses, research and educational collaborations, assessing proposals and products, mentoring entrepreneurs and startups, as well as the students, I believe. These are some of the things I think we could do to help each other learn from the knowledges and experiences of each other. Other opportunities at global scale include continue to develop or exploit automated systems approaches. That includes everything that we discussed already. And optimized cost and robustness, as I mentioned earlier. One thing I want to just mention here is that in these kinds of robotic solutions that I discussed in this lecture or seminar, multi-purpose machine becomes a big deal, because if I develop a robotic picking machine, it will operate in the field only 2 months out of a year. And investing a lot of money in these kinds of machines that remain idle for 10 months may not be the best financial decision. And that's why if we want to develop a multi-purpose machine that can harvest fruit when it is ready for harvesting, go prune trees, apply chemicals, do thinning, whatever else needs to be happening in the field, if the same machine with certain changes in the end effector can do all of these activities or operations, I think that becomes much more viable and commercially adoptable. I don't want to spend a whole lot of time talking about these other things. I think I already discussed a whole lot about how we collect data and how we want to focus on converting data into information. Connectivity is the big deal. Anything we do in the farms, and if we are trying to use cloud technologies or Internet of Things or cyber physical systems, connectivity becomes a big infrastructure that needs to be in place. And big data approaches for analyzing these different kinds of data. I already talked about plant level management earlier, so I don't want to spend time there as well. I just want to repeat that finding patterns from a set of heterogeneous data like images, weather data, yield, and historical crop management, and make decisions in terms of right input at right time, at right rate, and at right location or plant becomes an important goal as we go into the future of smart farming. Finally, agricultural control center is a concept I believe we need to move on to in a relatively longer term future, where most of the field operations are automated and we have people supervising these machines, operating them, maintaining them remotely, as I discussed in this slide here. With that, thank you very much. I think I almost took the entire hour, but I'm happy to take more questions and stay here longer as there need be. Thank you very much, everybody.
Well, thank you, sir. Sir, now I request you to please unshare your slides so that we can have the question answer and we can have face-to-face interaction with you. Yes, sir. Now I request the participants who are on the platform and who have listened to what extensive work Sir has done in terms of putting robotics into each and every operation that we go through when we are doing some work in the production system, in the agriculture system. So you can see how extensively robotics can be applied, the use of artificial intelligence can be applied, the use of various decision support system can be applied in every aspect, in every operation that is involved in the agricultural processes. So if you have any query, you are requested to please unmute yourself and put your query. Sir, meanwhile, we have a question from one of the participants. So the question is, so are you able to see the conversation box at your end? So you are mute. Please unmute yourself.
Yeah, I see the chat box here. Yeah.
Yes, sir. So there's one question.
Which is a suitable harvesting system for selective picking of cash crop, but it picks the more fruit at the same time? Good question. When we say selective picking, certainly it naturally leads to a robotic system where we can have a image processing system to identify which particular fruit is suitable or which particular vegetable is suitable for picking or ripe or whatever other quality parameters we want to look at. And that's another certain aspect of the robotic system. And selectively picking the one that we like, I think requires robotic picking solution. With the second catch kind of harvesting system, the one you saw with a couple of layers and on a stacking mechanism, we're also trying to aid some level of selectivity by applying right kind of frequency and amplitude of that signal so that only the ripe fruit or the ones ready for harvesting are released from the tree and others are not, or others stay intact on those tree canopies. So that's the direction we're looking at, but this is more challenging than certainly using image processing system to find out what we want to pick and then using a robotic system to do that. Certainly cost is an aspect, but I think we need to just work on creating more affordable solutions that might be helpful for our specific application. So let me give one example which might be relevant, and then we can move on. I was down in Peru and looking at mango planting systems, and these growers were talking about picking about 10% of the best fruit and shipping them to USA and other countries as an export market, the best of the best fruit, pick them at the right time, and then send them overseas. And then remaining one they could pick with the manual crew. And for that kind of situation, I think because this is a high value cream crop, 10%, 15%, 20% of the overall production, we might be able to use robotic system and be able to afford it, even though it's a robotic system, because again, we are selling it at a much higher cost. I don't know if that becomes relevant to some of the other crops, some of those produced in India, but just some thoughts there.
Well, thank you for the answer, sir. Because one of the participants, Dr. Kushwaha, have also raised his hand. So I request Dr. Kushwaha to, if you have any question, please unmute yourself.
Thank you. Thank you. Excellent presentation, Dr. Manoj. And we are working here in India in robotics. The main issue and problem in India, when we are presenting our robot or whatever the automation system, people are asking about the capacity of its function. That how much acreage or hectare it can be performed within a limit time, and what will be the expected cost of investment. That is a two issue mainly concerned during the Indian prospects. What is your answer about it?
That's a concern for farmers all around the world. Some of the companies that are trying to commercialize robotic picking machine, that the one I showed you in the presentation, there is another one out of California. We work with them as well. They are also trying to commercialize their machine, slightly different ways of picking. What I'm trying to say is that as long as these machines show an economic value to the growers, they will be interested and potentially adopt it, whether it is operated by the companies or operated by the growers themselves. In some cases, maybe service and whatever else. But going back to your question, these companies are trying to hit a per unit harvest rate. Like every fruit picked in US, manually picking would cost you about, looks like more like 15 cents or so, or maybe 10 cents. Can this machine pick in whatever speed, whatever way? Can it reach that kind of goals? And that's the way we're looking at it. We may not be there yet. We may be taking like 15 cents of fruit. It will translate into speed. I can do that mathematics, but if it is slower but cheaper, it might be doing the same thing. If it is more expensive but faster, it might be another model and achieving the same goal of picking every fruit for 10 cents or less. These machines that we're developing from your kind of a higher level perspective are doing about 2 seconds every fruit, 2 to 3 seconds every fruit, every arm. That means we have 12 arms and operating simultaneously, meaning every second we might be picking 6 fruit, which replaces about 6 to 12, 6 to 10, let's say, workers, depending upon their speed. Is that reasonable? 1 machine every 12 or 10 workers. I think in some farming operations, they feel okay with it. Maybe in others, we don't know how to operate the machine. It is complex. It costs a lot. You may need some maintenance. Replacing just 10 workers by this big complex machine, I don't like it. Those kinds of perspectives are there. I think over time we'll overcome these by reducing the cost, improving the reliability, and making these machines as seamless as possible so that farmers would not have to deal with any complexities by themselves. Going back to Indian context, I assume the economy of scale and the cost structure will be different. So we may have to adopt technologies differently. I don't know. It may be, again, as I mentioned earlier, it might be commercially viable for growers to pick only the 10% or 20% of their cream crop and send that to export market where they get as good of a value as whatever produced in the USA. But then remaining perhaps has to be done by the worker at this time. Anyway, some thoughts there. It's a difficult question, a question I get everywhere.
Yes, no. You have rightly you have explained. That is a future. It will be little bit costly. Just like a mobile system. Now mobile, it's coming with many features with a less cost. That can be happened in the future. Okay, thank you, Dr. Manoj.
Thank you very much.
Well, sir, there are 2 questions from yet another participant. He's a postgraduate student, I feel. So I think the answer to his questions you have already given, but if something could be added, because in terms of replacing, in terms of the labor and cost parameters, that will be replaced by this automation system by application of robotics in agriculture have already been dealt by you in your previous in answering your previous question. So if anything of that suppose means if anything is supposed to be added, please add.
So the first question about the cost, I think it's again labor cost issue. There are a couple of aspects. I covered most of them already, but I want to add this. Labor cost and availability will get worse in the future, and the technology, its reliability and robustness and cost gets better in the future. So even if it is not practically or commercially adaptable now, there will be a time where the lines will cross and will break even and start to use the machines. So I think research and development needs to continue, and we need to focus on advancing these technologies, make them more robust. And again, in the context of India, we also have to look at how we could make these machines more suitable for the situation at hand. It may not be the same machine that I am working on here in the US because the farming operations are completely different. So anyway, that's kind of something we need to keep in mind for our context in individual countries. Now, there is another question of the roles of students. A very good question. And I'm happy to hear that question, actually. From students, oftentimes I get a question of something like, how do I get an admission to a US university? So our role as students and somebody aspire to stay in higher education and research and education in the future, I think would be in a couple of aspects. One, continue to identify the challenges the farming industry is facing in our local context. Learn from the global situation, learn from the global research and development efforts, and understand the local context and local situation, and try to be creative in developing solutions that are applicable and meaningful and impactful for the context we have at hand. We discussed about those contexts already. I think anybody who is in this educational or area of research and development, I think need to keep that in perspective. It's slightly different than, for example, working in computer science, where context is not as important. For example, we're using same cell phone technology no matter where we are in the world. It may not be same thing with for example, developing a new crop, because what we develop for Washington State would not be producing as much or would not be resilient to the drought or insect or other pressure that we might see in Kerala. So these kinds of context-related research and development need to happen very thoroughly, particularly for agriculture, and that's why we need to be really creative and innovative to address the context related issues. Certainly, anybody interested in staying in this area is always a good thing for us working hard in this agricultural automation and robotic area, because it's very difficult to find motivated students and scholars to work in agriculture. It's changing a little now because we talk about robots now, and we talk about drones, and then we talk about AI and things like that. Not much different than electrical engineers, mechanical engineers, or computer scientists anymore. But even like 5 years ago, we did not know about machine vision very much. We didn't use a lot of technologies in agriculture, and things were different. It's changing, but I think it needs to change more, and people like you, motivated students, need to stay and contribute in this area. A long
Thank
answer
you for
to
the
a short
answer, sir.
question, but hopefully you got some.
Yes, sir. I expect that the intention with which the participant asked the question, it was clear. Yes, sir. Now, moving towards the conclusion of the session, because there were many take-home messages that we got after attending the session, sir, and specifically to the agricultural graduates, specifically to the people who are thinking of planning higher education in terms of finding applications of robotics in agriculture. This presentation, this session will really provide very good insight, and they will obviously be able to find out exactly how and what their role is and what their research problem might be, which they are going to focus upon in their future works. So thank you, sir, for joining in the late night hours and for giving us such a beautiful presentation where you started with putting the perspective of how the things have come up, and then coming ultimately to what are the challenges, what are the opportunities, and how we can contribute looking towards those opportunities. So it was a presentation that was totally weaved to our thing. Thank you, sir, for presenting this. Now, putting the final remarks, I request to UC Lohani, sir. Yes, sir, if you're there on the platform, for your concluding remarks and for putting up the vote of thanks. And meanwhile, I request all the participants to put their videos on so that we can have a group photograph with Karkee, sir. So moving towards UC Lohani, sir, for vote of thanks and concluding remarks, please.
Okay, thank you so much, Deepti. Thank you, Dr. Karkee. It's really nice presentation, and I hope that our undergrad students and some grad students I can see, they have learned a lot with your presentations. And now here we can see that what is the difference between the automation here in India and other countries and USA. So at least we have came to know some concept that we can adopt in our country, in our area, in research. So that is a very, very good, you can say, uh, delivering talk and concepts and ideas so that we can utilize those ideas and concepts here in India also. As we know that we are just going through some COVID situations, maybe if you will have to listen Dr. Karkee here in a physical mode, or sometimes it would be better that if you interact with the students directly, so the students will learn on something. So hopefully in future we will do that. So again, I'm thankful, very, very thankful to Dr. Karkee to deliver this talk to our students here. And I'm thankful to all the participants from the different institutions from Pantnagar University and different faculty members as the participants. I hope that this session we can continue in the next month also, and hopefully we will hear Dr. Karkee again with some other concepts on some other knowledge sharing basis. So, at last but not the least, I would like to thank Deepti. As I told several times, that she is an all-rounder because she is handling all the, what do you say, whether it is a seminar of agriculture, if it's a technology or veterinary, whatever. So she is all-rounder. She can handle each and everything. And without her support, I don't think that it would be possible to conduct these kind of events online. So thank you, Deepti, one more time to arrange this talk in a good manner. And one more time, thank you, Dr. Karkee. So share your valuable times and share your valuable knowledge among us. So hope to hear you in future very soon. Thank you, Doctor. Thank you, Deepti.
Thank you very much, everybody, and especially Dr. Lohani for again giving me the opportunity to